Well, welcome everybody once again to another interview here at Odin Noticias. This week we have the absolute honor to be speaking with Sir Anthony Leggett, a professor, physicist, and Nobel Prize winner. Professor Leggett, thank you so much for having us. It is a true honor to be speaking with you. The first question we would like to ask you is, how is a day in the life of Anthony Leggett?
Okay. Well, I normally try to get up sometime between 5 and 5:15 a.m. I get myself some breakfast and then take the bus into the university, to the physics department where I work. And then I start on the day's work, and the day's work can be very various. For the last few weeks, I've been teaching a lecture course, so one of the most urgent responsibilities is to try to prepare the next lecture. In fact, this is not so onerous because I've given this course a few times before, and so I do have very detailed notes prepared. But I have to go over to make sure that I'm familiar with what I'm going to say and perhaps correct a few things that need correction in last year's or last time's notes. Then I would typically go in mid-morning to the little cafeteria, and I usually I'm on the editorial board of various journals, which means I have to look at papers which have been submitted to these journals, and I give some kind of preliminary judgment on them, and so I usually take these papers across to the cafeteria where I have coffee and maybe a cake. Come back and work further again on the lectures, or perhaps on writing letters of reference for my students. That's something which I do a lot of, and which takes a lot of time. And then usually typically about 11:30, I go out to lunch. I usually have a light lunch at a different university cafeteria. Come back, sometimes sleep a bit. Luckily my office is quite suitable for sleeping if I need to. So, and then typically in the afternoon I would talk to my students. I don't have so many these days. I used to have more. At times I've had up to 10 students, but now it's down to a couple. And then, and typically I might go to lectures at lunchtime because I go to other people's lectures by visitors and so forth, because you have a lot of those. And in the afternoon, sometimes in the late afternoon, we have a sort of departmental-wide colloquium. I always like to go to that. One later this afternoon, actually, which I'll go to. And then usually about 5 o'clock or 5:15, I take the bus home. I usually try to do a certain amount of exercise on a sort of Nordic track type of machine. Take a shower. Of course, my wife is usually at home at that time. I have dinner with her, and we sometimes watch a television show and so forth, and then typically I go to bed about 9:30. So that's a fairly typical weekday, at least in my life.
Well, it sure seems like you're a devoted person to your work, Professor. Now, something we would like to learn is, when did you discover your passion for science? Was it at a young age, or did it come later in life?
Well, oddly enough, no, it came fairly late, actually. As a schoolboy, I had essentially zero exposure to science. I did have a little exposure to mathematics, but to all intents and purposes, I had no exposure at all to science. And it was only towards the end of my first undergraduate degree at Oxford that I gradually became interested in physics. This is rather surprising, because my father was in fact a teacher of physics and various other science subjects, but he never really tried to push me to get interested in it. It was only, in fact, when it occurred to me that I had, in some sense, to find a career, that I gradually became interested in science.
That is truly interesting. Now, Professor Leggett, you have been recognized as one of the leading researchers in low temperature physics. Could you please explain to our audience what this area of study is truly about? Because that doesn't usually fall into the common curriculum here in Mexico.
No, okay. Well, I mean, I guess it doesn't really in the UK or the US either. Low temperature physics, well, as the name implies, it's the examination of the physical properties of bodies at low temperatures. Now, you can ask, what is the point of going to low temperatures? And there is a lot of point because, crudely speaking, if you decrease the temperature, things which were disordered at high temperatures become much more ordered. A typical example of this would be, say, water molecules. At room temperature, of course, they form a liquid. If you take them down to zero temperature, then they freeze, become a solid. The solid is, in some sense, much more ordered than the liquid. The atoms are usually packed in regular arrays, whereas in the liquid they're moving around and jumping all over the place. Again, if you take certain magnetic materials, like, say, iron, at high temperatures, the iron, the little magnets, which you think of the atoms in iron as like little magnets, and at high temperature, they're all pointing in random directions. But if you cool it down past the so-called Curie point, then they will all tend to line up parallel. So again, we've gone from a disordered state to an ordered one. It's a very general feature. So, crudely speaking, the lower the temperature you can go to, the more ordered your system is likely to be, and therefore, in some sense, the easier it is to study, and the more spectacular some of the phenomena that occur. I've been particularly interested in the phenomena called superfluidity and superconductivity, which only occur below a rather low temperature. In the case of superconductivity nowadays, we can actually get it at temperatures about half of room temperature on the absolute scale. But superfluidity in a liquid requires us to go down to much lower temperatures, a few degrees.
And yes, of course, and now speaking of those same topics, in 2003 you were awarded the Nobel Prize in Physics with Vitaly Lazarevich Gisborg and Alexei Alexeyevich Abrikosov for, and I quote, pioneering contributions to the theory of superconductors and superfluids, which you were talking about a couple of seconds ago. Now, could you please explain what these two last concepts are about for our audience? What are superconductors and what are superfluids?
Well, actually, these are really not, they're really not two totally different phenomena. You can think of superconductivity as simply being superfluidity occurring in an electrically charged system, like a metal. Crudely speaking, both of the phenomena involve the ability of the system or parts of the system to flow without any apparent friction. So, for example, if I take a metal ring, suppose I take a ring of metal like, say, copper, which is actually not a superconductor, and suppose I induce in that ring a voltage, but the voltage is transient, that is, it only occurs for a short time and then dies out. So if I do that, then what will happen is that the voltage will produce a current circulating around the ring. But the current will only last, well, crudely speaking, about the same length of time as the voltage does. It'll die away. But if I were to do the same experiment with a metal which is superconducting, therefore at low temperatures, the voltage would die away, but the current will go on circulating forever. And there have been some very spectacular demonstrations of that. So, in some sense, that's one of the basic properties of superconductivity. And to do it with a superfluid, all you need to do is have to do essentially the same with helium. Helium is the only element which is superfluid under reasonably normal conditions. And again, you'd somehow stir the helium so to make it circulate around a ring, and at high temperatures, when it's not super fluid, it would start to circulate, but then slow down and stop. When it's in the superfluid phase, then it will essentially go on circulating forever. So that's one major component. The other that component is a bit more complicated to explain, but in the case of a superconductor, it has the consequence that it will expel a magnetic field. And as a result, you can get the phenomenon that's called superconducting levitation. And I've actually done this experiment many times. Yeah, if you take a small magnet and try to lower it onto a superconducting pellet, then it'll float. And in fact, it'll do more than that. It's actually more spectacular than that if you do the right kind of kit. And some of the kits I've used in the past have worked and some haven't. But what you can in fact do is to place the magnet on top of the superconducting pellet when the pellet is at high temperature, so at room temperature. So it's normal, not superconducting. And then you pour liquid nitrogen over the pellet, so you cool it, and eventually it'll cool enough to be superconducting, and at that point you actually see the magnet lift off from the pellet and float. And that's really rather spectacular when you see it.
That seems exaggeratingly interesting, Professor. But now I'd like to ask you, speaking about the award itself, how does it feel to win a Nobel Prize?
Surprising. I didn't really expect it, and, because it was very nice. Lots of nice things go with it. In particular, the actual Nobel celebration in Stockholm were rather nice and rather exciting.
And now I would like to ask you, what do you think is the future for science, Professor? What discoveries do you think will be made in the following years, decades, or even centuries?
Yeah, well, look, whenever anyone asks me that kind of question, I always give them the answer that do you know the famous, he's now dead, but the famous jazz musician Louis Armstrong?
Yes.
Yeah. Okay. So anyway, the story is that someone once asked Louis Armstrong where jazz was going, and his reply was, "Man, if I knew where jazz was going, I'd be there already." So I think it's not the same with physics or science more generally. I do think that one thing that's very, very interesting that's happened in the last, say, 15 or 20 years and is likely to continue and produce exciting results is the subfield, which we call quantum information, that is, using the weird properties or the weird features of the description of the world given by quantum mechanics to perform various engineering tasks. That I think is here to stay, and we'll certainly see some big developments along those lines, though again, because I can't really foretell what.
Well, thank you so much for having us, Professor, but before we go, I would like to ask you, what could you recommend for people watching us right now, young adults who are interested in studying physics or any science whatsoever?
I think the most important thing really is to follow your own curiosity. And if it's something you've observed in the world, as it were, which you don't understand, then try hard to find out how it works, as it were. Don't worry if people around you say, "Oh, that's sort of trivial. Everyone knows how that works." If you don't find the explanations they give you satisfactory, then just keep at it. And eventually, I think, even if it turns out at the end of the day that what you find out is already there in the books, or your teacher already knows it, doesn't matter. You've learned quite a lot by doing that, I think.
Well, thank you so much, Professor. It has been a true honor speaking with you.